Well, here we are talking about the second lesson in Chapter 7, and this lesson is about area in the plane. Okay, so we're used to finding the area between an x-axis and a curve, but now we're going to look within a plane. Okay, so what you'll learn about is now you're going to learn how to find the area between two curves. You're going to be able to find the area enclosed by intersecting curves. And then what happens when the boundaries are changing within the intersecting curves, how to do that. And last of all, up to this point, we've always been integrating with respect to x. Now we're going to integrate with respect to y. Okay, so let's connect what we're going to learn today to our prior knowledge. Now, our prior knowledge is we know that if we want to find the area between a curve and the x-axis, we started off using the idea of Riemann sums, and then from our definition of Riemann sums, we came up with the concept of the integral. So we knew that as the amount of rectangles that we drew between the curve and the x-axis increased, then the actual estimate was closer to the actual area. So we talked about, well, let's let the number of rectangles approach infinity, and if we multiply the height times the width of each rectangle, then we can closely approximate the area between the curve and the x-axis. And then this formed our definition of integral. Now, using this idea, we're going to still use the idea of Riemann sums and integrals, but now instead of the curve and the x-axis, it's going to be between two curves, okay? So here's an example where we have two curves. We have the curve F and the curve G, and we want to find this area between the two curves. Well, like we did before, we're going to draw rectangular strips between the two curves to kind of visualize what's going on here. So you can see the more rectangles I draw, the closer my approximation will be to the area between the two curves. Now, what is the height of each of these curves? Now we notice it's not between the curve and the x-axis, but it's between two curves. And my two curves that I'm finding it between is F and G. Now we notice F is the upper function, greater y value. So the height then would be the y value of the f of x function, take away the y value of the g of x function. And that would give me the area between the curves. Now, what is the width of these rectangles? Well, you notice I'm still drawing all of these rectangles with respect to x. Okay? Now, does the height change as you draw the rectangles in a different place? Well, no, we notice every time it's still f of x minus g of x, f of x minus g of x. So since we notice that, we can make it. And our conclusion is that if we partition our region into vertical strips of equal width change in x, then we know that the area of each rectangle will be the height times the width. Okay? So using Riemann sums, we take the sum of these rectangles, height times width, and as we approach infinity, we will get the actual area between the two curves. Okay, which will result in an integral. So, the formal definition for area between two curves using an integral is if f and g are continuous on a closed interval and g of x, the y values, are less than those of f of x, then we can say that we will be going from a lower limit of a to the upper limit of b, and then we will be multiplying the height times the width. Well, let's actually try it. Okay, so our first example. Notice we've got to find the area of the region. So the first step will always be to draw a picture and shade the desired range. So let's do that. So let's make a graph here, and I'm going to try to get some straight lines going on. So, whoa, there's my first y-axis. Oops, that's not what I wanted. Getting used to this little iPad thing here. Okay. And here's my x-axis. Okay. So now let us draw x squared plus 2. Well, we know that that has a y-intercept of 2. And then kind of goes like this. Okay. And now the second graph is y equals negative x. So we know the y-intercept is at 0 with a slope of negative 1. So down 1 over 1, down 1 over 1. And you want to try to actually make these somewhat precise because you will need this when determining your lower and upper bounds, okay? Yikes. There we go. Okay, and then the other regions we have here are 0 and 1. So x equals 0 is actually the y-axis, and x equals 1 is a vertical line at 1. So now, hopefully, you can see your shaded region here. So if I were to look at this section right in here is the shaded region, okay? So now let us draw in a rectangular strip, an arbitrary one, so that we can use that to set up our integral. So for example, there is the rectangular strip that we're going to repeat infinite times. So setting up the integral then, we are going to be going from, okay, we're going to be going from the lower limit where x is 0, the upper limit is 1, and the upper function we notice is the parabola, so it would be x squared plus 2, and then we're going to subtract that from the lower function, which is the line, which is negative x, and this is in respect to x. So now we've written our integral, now we evaluate, okay? So we'll combine like terms, so we go from 0 to 1, and we end up with x squared plus x plus 2 in respect to x. I'm going to open up a new page here and get myself some, so I can do my mathematics. So from 0 to 1 of x squared plus x plus 2 in respect to x. So we take the antiderivative. So I have 1/3 x cubed plus 1/2 x squared plus 2x, and we're integrating from 1 to 0. So now we evaluate. So I have 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1, and then that's going to be subtracted. Well, 0 substitute all of that is just a 0. So when I do the fractions and do the math, I end up with, let's see, I have 1/3 plus 1/2 plus 2, and if I make common fractions and such, I get 17.6 units squared because we're finding area. Okay? Great. Now let's look at another. Now, I wanted to come back to this example. This example is a little more challenging because the boundaries are going to change. Now, this is very important to have a precise graph. So we are going to find the area between cosine of x and sine of x, and they tell us the lower limit is 0 and the upper limit is pi-thirds. Now, we need to draw it so that we graph it so that we can see which is the upper function and which is the lower function. Now, because it's from 0 to pi-thirds, I'm going to have to kind of be precise and scale out this x-axis a little bit. So pi-thirds, and I know between 0 and pi-thirds there's a pi-fourth. Now, it might not be drawn exactly to scale here. And let's say that one is somewhere up here, okay? Now, we know that cosine starts at 0, 1. And we know that at pi-fourth it's radical 2 over 2. So we'll say radical 2 over 2 is a little bigger than 1/2. And then cosine at pi-thirds is 1/2, right? Okay, now let's graph sine. So this is kind of cosine. That's rough, I'm sorry. Okay, now sine, we know sine starts at 0, but sine at pi-fourth also is radical 2 over 2. But then at pi-thirds, it's radical 3 over 2. Okay, so sine looks like this. Okay, now you notice we have to find the area between the two curves. Now if you look here, we basically have the boundary changing at us at pi-fourth. So one of the regions is right here, and then the other region is right here. Okay, so actually we have two integrals here. So the first integral, the boundary grows from 0 to pi-fourth. And then you ask yourself, what is the upper limit there? Well, there it's cosine of x. And then we're going to subtract sine of x in respect to dx. Now, look at the second integral. Now here it's from pi-fourth to pi-third. Now what is the upper function there? Well, now it changes. The upper function is actually sine of x. And then the lower function is cosine of x in respect to x. Okay, now I'm going to let you use your calculators for this, and you can use your calculator to evaluate the integrals. And just to check your answer, you should get 0.4624. Okay, great. Now, what if it doesn't make sense to integrate with respect to x? What if we want to integrate with respect to y? That just means that instead of my rectangle having a vertical orientation, it has a horizontal orientation. For example, look at this sketch here where I have two functions, but if I were to draw vertical rectangles, it would be kind of awkward because look, it changes all the time, right? Like it's not going to give me a, you notice that the upper limit, the lower limit keep changing all the time. Whereas if I were to draw horizontal rectangles, it's much simpler, okay? But then we have to decide what is the height and what is the width. Same with this function. Horizontally oriented rectangles is much easier. And here. So when we look at this, like if I look at this example right here, we notice that the base here is changing between the g of y and the f of y. So we take the one to the right, so this length of the rectangle here is going to be the x value, f of y, subtracted from the x value of g of y. That would be the base of the rectangle. And then what would be the height? Instead of respect to x now, we notice it's respect to y. So notice we're taking, instead of the upper and the lower rectangle, we're taking the right function and subtracting it from the leftmost function. Okay, so then our new integral here is we go from the, again, the lower to the upper, c to d, but we take the rightmost function, subtract it from the leftmost function in respect to y. An example of this. So let's say that we have the functions, and I wrote in these functions, we have x equals 3 minus y squared is the first one, and then the other one is x equals y plus 1. And we want to find the area between these two curves. Well, let's take a look at what do these curves look like, okay? Well, 3 minus y squared, if I were to graph that and plot some points, we know that when y is 0, we would have x value would be 3. 1, 2, 3, okay? There we go. And let's see, when y is 1, 3 minus 1 is 2, okay? Now, when y is negative 1, it would also, 3 minus 1 is also 2, okay? And then we can keep continuing with this. The next function would be here at 2. Okay, so it looks something like this. Okay, now the other function, x equals y plus 1, we can write that in our standard slope-intercept form if that helps you, x minus 1. So then we know the y-intercept is at negative 1, and then it has a slope of 1. So it's going to look something like this. Okay, so we can see that our region here is bounded between the point negative 1, negative 2, and then the other point 2, 1. Now for this example, it would make more sense to do horizontally oriented rectangles. Okay, now the reason why is if I were to draw vertical rectangles, you notice then, let me switch to my little highlighter so I don't have to draw and rewrite over all this. So I would, if I were to make vertical rectangles, I would go vertical, 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 and the line is the upper function. But then notice here at 2, then, the parabola, or the square root function now is the upper function. So I'd have to write 2 integrals. Plus, look at these functions. If I were to write this in terms of x, in terms of y, that would be messy. Okay? It's easier to leave it in terms of x. So, to write this in respect to y, our integral then, now we look at the y values, is going from a lower y value of negative 2 to an upper y value of 1, and we take the function to the most right, which is the square root function, so we have 3 minus y squared, and then we're going to subtract that from the linear function, y plus 1, and it's in respect to y. Okay, now we just integrate the exact same way we've been doing. So let's combine some like terms here. So I would have a negative y squared minus y and then plus 2 in respect to y. And I do the exact same thing, use the anti-differentiation. So I have negative 1/3 y to the cubed minus 1/2 y squared plus 2y, and then I integrate from 1 to negative 2. And you can do the mathematics and check your work, and the answer then that you will get is 9/2. Okay, voila. So that is your lesson for integrating, finding the area between two curves.